present to you lecture 3B of the FIR filters course. Now last lecture we looked at the choose impulse response of a filter, but we only looked at the low pass filter. So last lecture we only looked at low pass filter impulse response. Now today we are going to look at this, but for high pass filter, band pass filter, and band stop filter. Stop. Let's get on. If you remember from last lecture, the FIR filter is based on the impulse response of an ideal filter. So let's look at that. FIR filter is based on the ideal filter impulse response. So for, again, revisiting the low pass filter, it has an ideal low pass filter looks like this: 1 at low frequencies, 0 at high frequencies. And this is an ideal low pass, of course, and the impulse response of this makes a low pass FIR filter. Now let's do the same for the high pass, band pass, and band stop. And now, of course, if you remember, that impulse response of this is sine 2 pi fc t divided by pi t. That's for the low pass, that is. Now, if you want to convert that to the computational form, it would be sine 2 pi fc n divided by pi n. N for sample, t for time. Okay, now let's look at the rest of the filters: the high pass, band pass, and band stop. Let's first look at high pass. Blue, good color. High pass. Now remember, the impulse response is the inverse Fourier transform of the frequency response. So if you draw a high pass filter, ideal high pass filter frequency response is 1 at high frequencies, 0 at low frequencies. This is frequency and amplitude. And remember, the impulse response is equal to the inverse Fourier transform of, well, the frequency response. Impulse response is equal to the inverse Fourier transform of the frequency response, which is this. So to do that, you usually integrate the frequency response. So that would look like this. So if you would integrate from infinity to minus infinity, the frequency response multiplied by e to the power of j 2 pi f n df, where f is obviously the frequency. Now, I won't go into any mathematical solving or derivatives because we're trying to keep it simple. So I'll just give you the exact answer of what this is. So the exact answer of what is the impulse response of a high pass ideal filter, it is the delta Dirac function time minus sine 2 pi fc n I divided by pi n. Now, what is this delta Dirac function? Well, we're going to discuss that a little later. Well, firstly, you should just remember that this sine over pi n, this is actually the sinc function, which we don't really look too much into sinc because this is not used on calculators. Your handheld calculator does not know what a sinc function is, but it knows what a sine function is, so you'll stick to sine. Now let's look at delta Dirac. Delta Dirac also looks like that. Delta function. Now, the delta Dirac is not something you can actually graph because it's an infinitely tall and infinitely thin spike. So on a graph, theoretically, I did say you can't graph it, but if you were to graph it and you really wanted to, it would look like a graph that goes to infinity. And, well, it's basically zero, isn't it? Because it's infinitely tall, so it goes to infinity. Infinitely thin, as in it doesn't actually have a thickness. It just keeps going on forever. It's just a very long, thin line that keeps going up. And that's all delta Dirac is. Now, if you're a computer, you're not going to be able to compute what is a delta Dirac function. You don't, infinity does not exist. Infinitely thin does not exist. So you have to come up with an approximation. So what is the approximation of delta Dirac t? Approximations. Delta Dirac time. Now, there are a long list of different derivations for delta Dirac. There is Gaussian, there is Boxcar, there are many more. Mathematicians probably know the longer list of all the approximations and their derivations. But if you look at one type of approximation, which is the Gaussian approximation, a variation of the Gaussian approximation. So let's look at that. So delta Dirac equals 1 epsilon. It's epsilon multiplied by the root of pi, that fraction multiplied by e to the power of minus t epsilon squared. Now don't worry about this scary looking equation. All you got to do is stick different values of epsilon. These values are epsilon. And by changing these values, you get a different or a better approximation. So a smaller epsilon, so smaller epsilon, like that, gives you a thinner and taller spike. A thinner and taller spike. So the smaller epsilon is, the better the approximation of the delta Dirac function. Remember, the delta Dirac is infinitely tall, infinitely thin. And in this equation, as epsilon approaches 0, you get infinitely tall, infinitely thin. Now, in reality, or on a computer, you cannot approach 0 because, well, you don't find infinitely tall, you don't find infinitely thin. That just isn't the way it is. However, if you stick a small value like, say, 0.001, that would also be 0.001, then you can get somewhat decent tall and decently thin spike. So smaller epsilon gives you a thinner and taller spike. Therefore, a smaller epsilon is a better approximation of the delta Dirac function. Now let's look at some graphs. Just before we look at those graphs, let's just t over here and t over here. They are just time, just to remove any confusions. Of graphing on Desmos, the different epsilon values. So let me just get a pen. Alignment looks good. Epsilon values. So if you have epsilon equals 0.1, you would get this graph here, where you can see that it's quite wide and it's not quite tall. It only goes up to, change the color, red. Only goes up to about 5.5. And the x-axis is, well, it's not exactly infinitely tall and infinitely thin as we want. You can change to epsilon equals 0.01. See a smaller value, 10 times smaller. And we get about a 10 times taller and around 10 times thinner graph. So you can see it's a lot taller. That's 50 and that's just 5. And there 0.2 is hasn't approached 0 yet, but if you look over here, it's like down there. A lot thinner as you decrease the value of epsilon. Now, if you want to go even smaller, epsilon equals 0.001. See, a lot taller, a lot finer. That's 0.2 here. This is 0.02, so a lot finer. The smaller your epsilon value, the better the approximation of delta Dirac function. Remember that a delta Dirac function, if it was real, would just look like this. Spike. Infinitely tall, infinitely thin. Let's move on, continuing back to high-pass filter impulse responses. Let's just rewrite the high-pass filter. So high-pass filter. Its impulse response, if you remember, is delta Dirac function minus sine 2 pi f cut off n over n. Now we approximated delta Dirac as should be 1 over epsilon pi multiplied by e to the power t divided by 0 epsilon 2 squared. Rub it out. So that is epsilon. So now, if you take this impulse response and graph it on a tool like Desmos, this is the graph you get. Something similar in shape like that, and that goes on forever. That is to minus infinity to infinity. Now just be aware this is graphed in time, not in samples. So this is samples, and this is in time, continuous time. I bet that's a wrong spelling of continuous, but you get what I'm trying to say. Now we did say we have to give an approximation based on the value of epsilon. So this value here, this value here. Now in this graph here, I've used an epsilon value of 0.01, so 0.01. However, you can see that the height of this spike is only to 1. Now, when we're dealing with impulse responses for a computer, we normalize it to 1. So the max amplitude should always be 1. So though it may not look like I've used an infinitely tall spike, well, we are normalizing it to 1. So that's the max amplitude you're going to get. Now, remember, FC here is a normalized frequency. Normalized frequency. So we're not putting 400 hertz here. We're putting 400 hertz in respect to the sampling frequency divided by 2. And that's our normalized frequency. Let's just rewrite that. Normalized frequency equals FC, our real FC cutoff. So if you wanted 400 hertz, you'd put 400 hertz here, divided by FS, our sampling, divided by 2. And whatever value you get here, which should be something in the range of 0 to 1. So that would go here. Yeah, and by the way, that should be pi n. Yeah, that's the high pass filter done. Let's look at the band pass filter next. Pass filter, impulse, that's not a pen. Band pass filter. Now remember, the bandpass filter looks like this. It has an impulse response like that from F1 to F2. Frequency in amplitude. Now it's 1 from the range F1 to F2. It is 0 elsewhere. Now this has a relatively simple impulse response. So we can say impulse response equals sine 2 pi F2n divided by pi n minus sine 2 pi F1n divided by pi n. Hopefully you can see all of that. Remember F2 is, change the color, blue is nice. Okay, F2 frequency there, F1 is a frequency there. Remember that F1 and F2 are still normalized frequencies. You never stick any other value other than 0 to 1 in here. Now remember that is n, as in n equals samples. But this graph here, which is the impulse response in time, for the bandpass filter, again, it's in time, not in samples. Now, we can again see that it ends at 1. I don't know if that's clear enough, but I think it's all right. You can see it goes to 1. This is a normalized impulse response. But yeah, there's not value, and the F1 value I've used for this graph is 0.6 and 0.1. Let me just write that down. So I've used F2 as a normalized value of 0.6 and F1 as a value of 0.1. These are just some random values I chose just to create this graph. Now, if you change the values of 0.6 to something else and 0.1 to something else, you'll basically still get the same shape. It doesn't change much, except you might get some scaling, maybe stint. Now, let's move on to band stop filter. Band stop. Let's look at the band stop filter. Band stop filter. Now, if you remember, the band stop filter looks like this. So this is the frequency response, frequency of amplitude. And you choose F1 and F2 as cutoff frequencies where any frequency in between F1 and F2 are 0. So ideally they should be 0. And anything other than in between F1 and F2, they should be 1. Just make that a little bit neater to see. Yep, F2. So yeah, that's the ideal band stop filter. Everything between F1 and F2 are 0. Everything away from that are not in that range are 1. And yeah, that's it. Now let's write the impulse response, the mathematical impulse response equation for it. Now the impulse response looks like this. It's sadly a lot longer. Response equals to delta Dirac minus sine 2 pi f2n over pi n minus sine 2 pi f1n over pi n. So remember, f2 and f1 are normalized frequencies. So let me just make sure that's written down. Normalized frequencies. And for an f2 value of 0.6 and an f1 value of 0.1, this graph is given. Now you can choose any normalized values for f2 and f1. I just chose these two values, 0.6 and 0.1, just to show you the shape of the graph. Now, again, the graph is normalized. So it only goes up to 1. The max amplitude is 1. By changing these values, 0.6 and 0.1, you'll just get different scaling, x and y scaling of this graph, but the approximate shape is still the same. Remember that delta Dirac, I'll change the color to red, is equal to 1 over, or approximated to 1 over epsilon multiplied by roots pi, all this multiplied by e to the power of 1 over t divided by epsilon squared. Now for this graph, I've used epsilon as 0.001. Now, of course, the smaller epsilon equals better approximation of delta Dirac. That's just from previous slides, of course, but there, just put that there in case you forget. Smaller epsilon, better approximation of delta Dirac. Now, again, we use n over here. this just means samples, n just means samples, like for the rest of the impulse responses. Well, this is time. Well, this is graphed in t, as in time. Now, if I rub this all out and show you what the difference would be, so we're going to look at what is the difference between n and t on the graph. So if you set t equals time and n equals samples. Now, I've used time because it shows you a better shape, but if I draw a graph, so that's our orange graph, where the blue will be any random impulse response, any random filter. Now, this blue graph is in time. Now, if I was to draw this in n, well, that is just these exact values here. We just draw it again, it's symmetrical filter is, so it goes on both sides, negative values too, etc. So if you draw the blue graph, that is in time, but if you were to draw this in just discrete time n, so n would just look like these, some dots. So if I was to draw just n alone, it would just look like that. And typically, sometimes you see it drawn on MATLAB or Python as lines, just to show its discrete nature. Overall, the shape is about the same, it's just that you're picking discrete points of the graph. Now, one thing you must memorize is that this is a symmetric filter, so if you have a really high order filter, that means it'll have more coefficients, that means there are more values of n. Well, it goes on both sides here. You must have the negative portion symmetric with the positive portion. Remember, that is for it's a linear phase. That gives it linear phase characteristics and probably some other important characteristics too. Now, the next lecture we'll be looking at window functions, because remember, this goes on for to minus infinity to plus infinity. Remember our filter, so it's finite. That is finite. It does not go on forever. So next lecture we look at window functions. Please subscribe and like. Thank you. See you next time.